All right, welcome to our lecture on contrast. We're going to be talking about why contrast matters, how we use contrast, and pretty much the reasons why we have to worry about it when it comes to our parameters. So first thing we're going to do is kind of define contrast here. We're going to talk about it's the difference in color between two pixels. So if we have two different pixels that we're looking at, right, and these two little pixels here, one is very dark, we could say it's black, and the other one has white, then this is a contrast. It's the difference in shade between these two. The difference in color, you could say, but it's black and white. So it's the difference in shade between these two different pixels. That's what contrast truly is. And we have pretty much two types of contrast. We have low contrast, and then we have high contrast. Low contrast, we have lots of shades of gray, because contrast itself is the difference in the shade between one pixel to the next. So if there's not a lot of difference in the shade between two, then we can see that that is where we're going to have low contrast. If there's a lot of difference between two shades, where you can see there's a big jump in the shade from black to white, then you have high contrast. The highest contrast you could possibly have would simply be a black pixel next to a white pixel. That is the highest contrast that you can actually have. So in MRI contrast, we usually define this by talking about our T1, our T2, our T2 star, and our proton density weighted images, and how we get to those images, and how we manipulate parameters in order to have the contrast that we desire. So now that we know we have low and high contrast, we can see that some images are better with low contrast and some are better with high. For instance, high contrast. When we would want to use high contrast, let me change my pencil here. We would want to use high contrast for something like an MRA. For instance, a time of flight of the head is going to yield pictures that have very bright vessels and everything else will be very dark. This is very high contrast. On the other hand, if we were to look at something like, say, for instance, a proton density weighted image, we would have lots and lots of shades of gray, because some fluids are bright, some fats are bright, some muscle is bright. So we have low contrast with a proton density weighted imaging because we have lots of different shades of gray. So contrast is one of the most important things when it comes to figuring out what your image is going to look like. Usually you can sacrifice signal or time or anything else, but contrast has to be dead on. We need to make sure that we're producing the right type of images for the radiologist to be able to read it. So that's kind of our scale of contrast, and that's what contrast is. Now, if we have a pixel that has very, very, very bright, then what kind of signal does it have? It'll have high signal. Right. And if we have a pixel that is very, very, very dark, it will have low signal. So when we're looking at contrast, we are manipulating how we're going to get signal from different tissues. And as different tissues make up the different pixels that end up giving us the final picture. So all of this contrast here, all of what it's doing here is telling us how much signal is within one pixel at that one point in time, based on what we choose for the parameters. So the parameters we have for contrast are TR, we have our TE, TR, our TI, and our flip angle. Now there's other things that can affect it, but as far as the registry goes and as far as this course goes, these four are the parameters that will change contrast. All right. And that's usually when you are going to be getting into my quizzes. You're going to see that every quiz that you take is going to have parameters on it. And it's good to learn now which parameters affect which aspects of scanning. So for TE, this is controlling. If we were to be looking down at our proton, this will be our hydrogen proton. Hydrogen proton. We're looking up, we're looking down at it. So all of this entire circle right here is going to be the transverse plane. All right, this is a top-down view of how we normally look at atoms. So TE is the amount of dephasing that occurs before we use the 180-degree RF pulse in a spin echo, or a gradient in a gradient recalled echo, how much dephasing is allowed to occur. So if we have a short TE, not a lot of dephasing occurs. Everything starts all together. Then the magnetic moments begin to separate. We apply the 180 degree RF pulse. Everything comes back together. And when everything is lined back up, that's when we use the coil to record the signal. So TE is a measure of how much dephasing we're allowing to occur, how much dephasing is happening. Now this dephasing affects fat and water. The more dephasing that you allow to occur, the brighter that fluids are going to be. And the less dephasing that you allow to occur, the darker fluids will be. So when it comes to TE, as TE increases, we also increase the signal from fluids, which we call T2 weighting. As the TE decreases, we decrease the signal from fluids, so we decrease the T2 weighting. This should be showing that it is increasing. All right. Now this is very important. We can kind of lose the part about fluids, and we can just look back and say TE increases, T2 weighting increases. TE decreases, T2 weighting decreases. All right, pretty simple. Please note that TE has nothing to do with T1 weighting and T1 contrast at all. TR will control T1, TE will control T2. This is very important for the registry and very important for the quizzes that you'll be taking in this class, because I'll ask a question and say, how do you increase T2 weighting inside of an image? The correct answer is to increase TE. It is not to decrease TR, which sometimes people get confused with. So let's now talk about TR. With TR, we are now looking at a side view of our proton with a longitudinal transverse plane. It's how much magnetization we allow to relax back into the longitudinal plane before we sample. All right, so the TE is the time from the 90 degree until the echo, and the TR is the time from the 90 until the next 90. So two different time periods that we're controlling with these parameters. So with the TR, as we increase our TR, we end up seeing a drop in T1 weighting. Fats actually become darker. And as we decrease TR, we have an increase in T1 weighting. Once again, T1 weighting has nothing to do with TE. TR controls T1, TE controls T2. Now these are the two biggest parameters we have inside of contrast, right? Because TR and TE, those are the big ones. Those are what changes a lot. Next we'll talk about TI, that's the inversion time. So if you remember from physical principles that for inversion time, TI is the time from the 180 degree inversion pulse to the 90 degree excitation pulse in a pulse sequence. The length of the TI will determine a couple of things. We can do pretty much three things with an inversion pulse. We can either suppress fat, we can create more T1 weighting, or we can suppress fluids. If we have a short TI, we end up suppressing fat. A medium TI will increase our T1 weighting, and a long TI will suppress fluids, which we also will call the sequence a stir. Short time inversion recovery. Medium one, usually this is just done brain imaging, and you may not see it that much these days. The long TI with suppressed fluid is a flare, or fluid attenuated inversion recovery. All right, so short tau inversion recovery, fluid attenuated inversion recovery. Long TI, flare. So why we consider TI a part of contrast is that we are suppressing certain contrasts, so we are getting rid of the signal from fat or from fluids, so it is changing the contrast, or we can increase the amount of T1 weighting. Finally, we have the flip angle. The flip angle is much harder to define. We can't simply say a lesser flip angle gives us one type of contrast and a greater flip angle gives us another type of contrast. It's more a question of the flip angle for the gradient recalled echo combined with its TR and its TE will end up resulting in different types of contrast. So we will talk through a lot of different sequences later on, and when we start talking about stuff in the abdomen, we'll talk a lot more about contrast and the flip angle and how it affects contrast. For the moment, all you really need to know is that the flip angle is almost always going to be 90 degrees for a spin echo pole sequence, and it will only increase it'll only change when we do gradient recalled echoes. And this is pretty much the information we need to know for contrast from this week's reading.